Hello everyone, this is Arezoo Rajabi from University of Washington. Today I'm going to present our paper on free adversarial examples for super-resolution convolutional neural networks. Thanks in advance for your time. Before introducing our approach, I would like to talk a little bit about super-resolution convolutional neural networks or SRCNNs. SRCNNs are a type of deep neural networks that take very low resolution images and generate high resolution images. SRCNNs pose a serious privacy threat. For example, many applications or online services don't share high resolution images, but they share low resolution images, since they think the low resolution images are not classifiable. However, as shown in figure on the left side, an adversary can use SRCNNs to generate high resolution and classifiable images for her classifiers. As an example, we use SRCNNs to generate high resolution image from a very low resolution face image and then gave it to the face recognition model of clarified.com. As shown in this figure on the right side, the face recognition model recognizes the face correctly. SRCNNs might affect the performance or practicality of two image privacy approaches. The first approach is the perturbation-based image privacy methods like UEP and KRTIO that published in PETS 2021, since these approaches have never taken SRCNNs into account. The other approach is thumbnail preserving encryption methods, which generate an encrypted image with an exact low resolution of its original image. There are two main questions that needed to be answered. First, adversarial perturbation-based privacy methods practical? Second, can we share all low-resolution images? To make these approaches practical, we need to learn adversarial noise for low-resolution images such that the generated high-resolution images from them can fool classifiers. In this paper, we focus on adversarial or perturbation-based privacy preserving methods. These methods are becoming popular for two main properties of adversarial images. Adversarial images can fool unknown CNNs, means if they are trained on CNN A, they are able to fool CNN B. Therefore, the knowledge of the adversary CNN classifiers is not required. They are recognizable for human but not classifiers. Therefore, users can browse and search over their images. As a result, we focus on how we can preserve these two adversarial images properties when they are processed by SRCNNs. Generating low-resolution adversarial images with these two properties is shown to be feasible by joint optimization. In this scenario, both targets SRCNN and classifier are known and their hyperparameters are available to users. Therefore, the user can learn adversarial low-resolution images with the property of fooling the target classifier. However, this scenario is not realistic since the user don't have any knowledge about the adversary's SRCNNs or classifiers. Therefore, the question is that if users use their own SRCNNs to learn low-resolution adversarial images, do they fool unknown SRCNNs or classifiers? If yes, how to update the adversarial perturbation-based method for joint optimizations? Before introducing our approach, let's review our assumptions. An adversary has only access to low-resolution images. User can train a local CNNs to learn adversarial noise or perturbation. Users don't have any knowledge about the SRCNNs that might be used by an adversary. User goal is to add survivable perturbation to their low-resolution images such that the generated high-resolution images by SRCNNs are not classifiable. In this work, we aim to answer the following questions. Does adversarial perturbation or noise train only on CNN classifiers survive through SRCNN, or do we really need to upgrade the adversarial noise learning methods to consider SRCNNs? If yes, how can we learn survivable adversarial perturbation for low-resolution images? Before answering those questions, let's define survivability for adversarial images. An adversarial low-resolution image survives through SRCNNs if its super-resolved image can fool unknown CNNs. We use the metric of transferability to assess this property. Transferability measures the ratio of super-resolved low-resolution images that can fool unknown CNNs. The other property we considered for survivability is recognizability. The adversarial images are not recognizable for classifiers, while they are perceptually recognizable for humans. This is the main reason for the popularity of adversarial-based image privacy approaches. Consequently, we would like the super-resolved images from low-resolution images to be recognizable for humans. Therefore, they can browse their images. We use similarity metrics to measure how well this property of adversarial images is preserved by going through SRCNNs. Till now, we talked about survivability of adversarial low-resolution images, and now we are going to talk about the approaches one can use to learn low-resolution adversarial images. The first approach is to train adversarial images on high-resolution images and then downscale them. The previous adversarial or perturbation-based methods learn adversarial noise on high-resolution images and assume the user has access to a large CNN. The main question about this approach is that if downscaling the adversarial images reduces their impacts or not. The other approach to generate low-resolution adversarial images is to train them directly on a small CNNs. When we say a small CNN, we mean they are trained on low-resolution images with a limited number of classes. Here the main question is that if the low-resolution adversarial images trained on a small CNN can make SRCNNs to generate unclassifiable high-resolution images or not. Now we plan to assess the survivability of low-resolution images generated by the first approach, which is downscaling high-resolution adversarial images. The first metric to assess the survivability of these images is transferability. To measure transferability, we considered both white box and black box access scenarios. In white box scenario, we train adversarial images on original high-resolution images using a CNN, let's call it CNN A. Then we downscale them. After that, we fed the CNN A with the super resolved images generated by SRCNNs, and we measure the transferability. For black box scenario, we gave the super resolved images generated by SRCNNs to another CNN, let's call it CNN B, and then we measure the transferability. Here we use two large CNNs trained on ImageNet dataset, call it ResNet 150 and ResNet 101. Also, we used fast gradient sign method for learning adversarial images with different values of epsilon. As you can see, transferability of adversarial images for those scenarios is comparable. The other question that we wanted to answer is if the user hypothetically has access to the output of SRCNNs and adds the adversarial noise learned on the original high-resolution images to the output of SRCNNs, then the transferability improves or not. Our experiments show that the noise generated by SRCNNs might reduce the impact of adversarial noise. Therefore, having access to the output of SRCNN doesn't help here. For example, for car X4, an epsilon 25% for black box scenarios. The transferability is around 75%, while adding the adversarial noise directly to the output of SRCNNs decreases the transferability to 31%. The other property we consider for survivability is recognizability of super-resolved images from low-resolution adversarial images. The adversarial images are not recognizable for classifiers, while they are perceptually recognizable for humans. As is shown in the figure on the right side, the super-resolved low-resolution adversarial images are similar to the original high-resolution images. Our experiments show larger amount of adversarial noise leads the super-resolved images to have lower quality, but they are still recognizable. We use the similarity matrix to measure how well this property of adversarial images is preserved by going through SRCNNs. Please read the paper for more information. Also, we evaluate our second approach for generating low-resolution adversarial images, which is directly learning low-resolution images on a small CNN. In this scenario, a user needs to train a small CNN to learn adversarial low-resolution images. As is shown in this table, for a small value of epsilon like 3%, the transferability is high and more than 95% for a black box scenario. Also, figure in the bottom shows that super-resolved images are recognizable. We received a great question from reviewers during the rebuttal phase. They asked how might be the transferability of low-resolution adversarial images be affected if the adversary uses a robust CNN. A robust CNN is defined as if classifier returns label Y for an input X, it returns label Y for any input X plus delta for all delta less than R. We observed in this scenario, if the user utilizes a non-robust CNN, she cannot learn a transferable adversarial image. Therefore, we use two pre-trained robust models on ImageNet dataset as users and adversary CNNs and evaluated both black box and white box scenarios. Our experiments show that the super-resolved images have comparable transferability to the original adversarial images. For example, for car X2 in white box scenario, we got 33% transferability for original adversarial images and 27% transferability for super-resolved images. Note that for white box setting, both adversary and user use the same robust CNNs, which is a robust CNNs with the L2 norm of epsilon equal to 3. We observed similar results for black box settings in which the adversary uses robust CNNs with the L infinity norm of 8. We can conclude if users utilize robust CNNs, then they can learn survivable adversarial images against an adversary with the robust CNNs. Briefly, in our paper, we show that adversarial noise survives well in dynamical adversarial examples through SRCNNs. Adversarial noise trained directly on low-resolution images can survive through SRCNNs. Robust CNNs can reduce the transferability, but if users utilize a robust CNN, then their transferability will be high. Thanks for your time and attention. If you have any question, I would be happy to take them.